So I might actually start. Please welcome Professor Dorothy Bishop. She's a Wellcome Trust Principal Research Fellow and a Professor of Developmental Neuropsychology, that's a big word, at the University of Oxford. And she's also leading meta-research, and she runs very popular blog, Bishop Blog. Today, she's gonna give us a talk on why we need cumulative science. Please, Dorothy.
Thank you very much, and thanks for inviting me. It would be much nicer to be in Australia than in Oxford at the moment. I'm rather sorry that I'm actually sitting here in cold, dark Oxford, but glad to at least share some thoughts with you on why we need cumulative science. So the idea of science being cumulative, you could argue, well, this is obvious that we need cumulative science. Everybody knows that. It goes back to Isaac Newton, who was very famous for actually not validating other people's points of view about anything very much, but he did at least say at one point that he'd seen further, it's by standing on the shoulder of giants. And there's this idea that all of us will take the prior scientific body of work and build on it, and that way we go sort of onward and upward. What concerns me is that I think we often think we're doing that, and we're not. And I time and time again meet early career researchers, particularly when talking about reproducibility issues, who have tried to build on a previous literature, assuming it's a solid foundation, only to find that it's not. And so that there are phenomena in the, certainly in the psychological literature, but way beyond psychology across science, where what you do is you start thinking, well, I'll take forward, say a study on ego depletion. People have been talking about recently on Twitter, describing their PhD experiences where then you can't replicate the basic effect, let alone take it further. But it takes you perhaps 3 years of your life to discover that. And you've spent a long time thinking it's you doing something wrong, rather than that the actual finding's not solid. So this is, I think, widespread and a real big problem. And I want to discuss why we have this big problem. This paper I love, and I recommend it to anyone. It's a bit technical, by Carl Bergstrom's group, headed up by Nissen. And they talk about exactly this phenomenon, which they describe as the canonization of false facts. So canonization, they define as the idea that you get to the point in science where some claims become so widely accepted as true that you take them for granted. You don't feel this is something that needs to be any further evaluated. It forms the basis of where you go next. And typically this will only happen when you've got a lot of supporting evidence from different directions. And I was thinking about it, I'm not really a Bayesian. I fiddle a little bit with Bayes and try to understand it. But from a Bayesian point of view, it's a basic idea that you've just got a really strong prior. Your prior is so strong that you would need overwhelming counter evidence to shift to any sort of other view. So that's canonization. And the problem is this is happening prematurely. I tried to draw a diagram of what I thought canonization looked like, just because obviously it's not either or. There's a whole range of different amounts of confidence one has in findings. And sometimes you're overwhelmingly confident in favor of something like the Earth is round. I would say now global temperatures are increasing, we're overwhelmingly confident in, although there may be some people that dispute that. But it doesn't have to be the big questions. Also, caffeine makes you wakeful, something like that. If I did a study and said caffeine sends you to sleep, you'd be very skeptical about that because you've got tons of experience that it makes you wakeful. At the other extreme, we've got things we overwhelmingly would want very strong evidence for because the evidence against them seems strong, like extrasensory perception, which has been actually debated in psychology as to whether it's real or not. Most people feel it overturns the rules of physics and therefore we should have a very, very strong negative prior to not believe it, or astrological forces determine your fate. And of course, the areas of science where most of us are working are somewhere in the middle, what the clinicians would call equipoise, where you're really not certain, which is why you need to do experiments and try and work out what is the case. And earlier in the year, we had a lot of toing and froing with hydroxychloroquine, whether it was effective or not against COVID, very topical thing. And that is moving up and down this green line as different studies occur. And I think it's moving into the red zone at the moment. But you have to do quite a bit of research before you know how much confidence you have. Now, this has real implications. If something gets canonized, you won't tend to get further research on it. because if you just confirmed that the Earth was round or something, nobody would think that's worthy of publication. It's obvious we know it. On the other hand, if you reject something that's been canonized, also people just won't believe you, and it may be difficult to publish something. And I know there are people early on who found, for example, in the psychology example, they didn't confirm ego depletion, and people just said, well, you're not doing it right, because we know ego depletion exists. So the new studies tend to assume the canonized facts, don't test them, and then we try and build on them. Now, Bergstrom and his group, and this Nissen paper, this is a quote from that paper, said, well, you know, quite often people say there's lots of studies, which therefore is the reason that we think something is believable. But if you've got multiple studies to establish a fact, it's no panacea, because the same processes that allow publication of a single incorrect result can lead to the accumulation of sufficiently many incorrect findings to establish a claim as a fact. So what they're saying is there are processes that mean we think we've got enough evidence when we haven't. And the one they emphasize is publication bias, which of course is very well known as something that does tend to distort the literature. But I think what I liked about their study is that they actually do some simulations and some formal analysis to show just how this works and how serious it is. So we all know about publication bias. It's been known about since the 1970s. Greenwald talked about prejudice against the null, that journals won't tend to want to publish null results, and concluded that the publication system may be regarded as a device for systematically generating and propagating anecdotal information. And the term, the file drawer problem, was coined by Rosenthal in 1979, many years ago, describing how lots of us have got file drawers stuffed full of experimental data from studies that we didn't ever publish because they were null. These days, it's not a physical file drawer, it's just a folder on your computer. Now, the way they analyzed it in this paper, it looks for a fearsome diagram, but basically they noted that you can really compute the probability of having a study that supports or fails to support a hypothesis versus a null hypothesis just on the basis of basic knowledge of your alpha level, typically 0.05, and the power of your study, which is going to tell you how likely you will see a positive result if you have underlying data that's true. And you can work through this diagram and realize that if you actually observe supportive or non-supportive data, what's the relative likelihood that it comes from a null distribution or whether that your hypothesis was true. But they add to this process this final step, which is the probability that you publish, and showed that if you then find that you've got a null result, and that increases the probability that it doesn't get published, and then you sort of can go through a loop where you build on prior evidence, you can rapidly get to a situation where you think you've got very strong evidence when you haven't. I've got my own way of demonstrating this because theirs is quite technical, but just it's a thought experiment. So you've got a series of experiments and testing a treatment for, say, COVID, let's be topical, and we think there's a 50-50 chance that it will work. We're going to adopt an alpha of 0.05 because everybody does, and we're nicely powered at 0.8. And you then, under those assumptions, you observe 5 studies, a positive one, then a negative, 2 positives and a negative. So if you got that pattern of results, how confident do you think you would be that the treatment is actually effective? Just take a moment to think about that. Would you think it's very likely to be ineffective? It may be effective, but it's unclear, or it's very likely to be effective, given this particular assumptions about alpha and the power. So you had to think very fast, but let's have a look at it. You can actually plot the sort of the way this evidence accumulates, which is what I've done on the right-hand side here. And it shows really that the treatment's very likely to be effective in the sense that the log odds of the real effect is 54 times more likely than the null hypothesis being true. That's what that log odds converts to. So I put a dotted line at 4, which is a sort of, you could regard as a threshold for beginning to be confident that something actually works. So this is a point that Dan Larkins has made. We often, I think most people would pick B, but actually this isn't bad evidence at all to get 3 out of 5 studies coming out that way, given your alpha and your power. But what about, oh, sorry, and I'll just illustrate how I do those computations. So your alpha level determines the columns here under H0 is true. So if there's a null hypothesis is true, how likely is a null result or a positive result? If the effect is really there, then it's your power that determines how likely you see those two sorts of results. And what, of course, you don't know what's true, but you can observe null or positive. So you work along the rows here to work out the relative likelihood of one hypothesis versus another. That's just those computations. And we're starting with a prior of 0 because we don't know which is work. But then suppose we do the same sort of logic now, and we've got more trials with a longer sequence where we get a positive 1, then 3 negatives, and a positive and 2 negatives, and a positive and 3 negatives. That once again, that should shift your confidence in the intervention, but does it shift it to the point where you think it's maybe worked, maybe doesn't work, or to be very ineffective? In fact, if you do the same sums, which in the interest of speed I will, you move in the opposite direction to log odds of -4. So you've shifted from one extreme to the other, from thinking that the treatment is 54 times more likely to be working than to have no effect, to the exact opposite. It's 54 times more likely to have no effect than to actually work. Now, the key point here is that this scenario B, if that is true, but you drop half the null trials, you've got scenario A. So if you remember scenario A, where everything was trending up to be marvelous evidence, then you are just leaving out and not publishing and not mentioning about half those null trials. You get to the point where you think you've got very strong evidence. So omission of trials can really shift you from a position of extreme confidence that the thing doesn't work to extreme confidence that it does work. It can have a really big effect. And this is why in clinical medicine we have trial registries now, because the medics became aware that if you just accumulate evidence for things working and never see the null studies, you get very misled and people may die or get the wrong treatment. This actually was documented as happening in real life, because you may say, well, do we really drop half the negative trials? This is a beautiful demonstration from De Vries, who looked at clinical trial registries. So where things are registered, you know they've been done and you can check out what the results were. And what you see here are going across the diagram are studies in red that had null results and in green that had results showing treatments were effective for treatments for depression. And what you see is a great drop off of the red ones, but not the green ones, going from the first to the second line, which is whether the trial was in the registry, and then the second line is whether it was published. And then you get more bias because you get people who also distort the outcomes and perhaps pick a different outcome from the one that they had registered to make it look positive. So you're losing the null data. And we only know that this is happening here because there are registries, but in most areas of science, there's no registries. We don't ever see the null data. So there's tons of possibilities for us distorting our literature just by leaving stuff out. Then we've got another related phenomenon, but which has had much less attention, which I'm getting really interested in, which is citation bias, which arises partly as consequence of our tendency to have confirmation bias. We only cite things that agree with our point of view. So this study went on to look at how studies were reported. And one thing that happens to studies is they get spun, which is that people report a study that didn't actually show a positive effect as if it did. And then you look at how often the study gets cited. And you find that what they've shown here is the size of these circles is related to the number of citations. And it makes you feel like it's like an evolutionary process. And these poor little red dots at the top are studies that got a null result, survived getting published, didn't get spun, but got to the end, and then nobody cites them. Whereas a study that finds an effect gets cited. So this actually makes matters even worse, because when you read the literature, you get an even stronger impression that things work and that null results don't occur. And you can only really overcome this if you do a systematic review. And even then, you're not going to see probably a lot of the studies that don't get published in the first place. So we've got a massive problem in our scientific system that we're distorting to find positive effects. It gets worse still, because we then have also p-hacking. And a lot of people think of p-hacking as a not too serious thing. Everybody does it. We're always trying to just find this significant result in a study that we do. But this actually amplifies these effects even more, and I'll show you how. So those, I suspect most in this audience will know about p-hacking. Psychologists love to talk about it, and the way I try and explain it is using poker. So if you've got a hand of 5 cards, in most of probability theory was actually developed from people studying games of chance, because it's very important to know how likely different hands are. This is one that's got a likelihood of about 1 in 50 of occurring by chance if you just get a random set of cards. And so I could say, well, I'm a magician. I can actually control the cards by the force of my mind. And without any cheating, if I just think hard enough, I can deal 3 of a kind. And I do that in front of you and you think, wow, you know, Dorothy's incredible. But you'd be much less impressed if I went around the room and did it with 50 people and only one of them got 3 of a kind, because that would be exactly in line with what the chance would predict. And this is really just to say, you can't just say, oh, this is an unusual result without understanding the context in which it was obtained. And if it was obtained by looking at many, many results, then it's much less impressive. This is another way of trying to demonstrate it, because I think there's people have real trouble with this, and they tend to think of a p-value as equivalent to an effect size. But here, this is just simulated data from a random normal distribution, of thinking that what we're doing is we're testing 16 compounds for their ability to improve memory in rats. And if your score is above the line, your memory is improved significantly if you just do a single t-test on that particular compound. So those are the conventional asterisks for 0.05, 0.01. And you can see that in this completely random data that I've distributed, there's 2 things that pop up. And if you were naive, you might think we should do further research on compounds G and J because they look significant. But the point is that this test of significance is totally inappropriate in this context, because if I'm asking, is compound G significant? That's one thing. But if I'm saying, are any of these 16 compounds significant? I'm going to be interested in any one that passes the 0.05 barrier. That's a different question. And the likelihood of actually getting a positive answer is not by chance, is not 1 in 20. You can actually work out it's more like 60%, because you're really having to compute what's the probability that nothing is significant, 0.95 to the power of 16, and subtract that from 1. So actually, you could, if you did a study like that and you pulled out your significant compound and thought you were working with an alpha level of 0.05, you might actually be working with an alpha level of 0.6. In other words, your likelihood of getting a false positive is as high as 60%. And if you follow through the same sums that I did before for that graph, that's what it looks like in terms of evidence. Flat line, pretty much. You have no idea whether this thing works or not if you've been p-hacking, because you really distorted your alpha level in effect. And so you think you've got conclusive evidence because you think you're working with a 0.05 alpha level, but you're not if you're p-hacking. P-hacking takes many, many different forms, things like dividing things post hoc into subgroups and so on. Lots and lots of ways you have flexibility in your analysis, and it creates massive problems. And it gets still worse. Shifting goalposts is something that I'm also getting particularly interested in. And I won't go into detail here because of time, but I've got a longer talk on this topic of biomarkers, where this happens a lot. So people get very interested in associations between either neurological or genetic variants and things like people's cognitive abilities or clinical conditions or whatever. And you can follow through literatures like this and see that, you know, there was like an initiating study that came up with some association, which was usually p-hacked. When you look at the context, looks very plausibly p-hacked. And then that spawns a literature. People do a lot more, and they forget all the null studies, and the pink ones come up, and they spawn yet more. But the interesting thing is that the theory mutates as it goes through this cycle, because people don't actually succeed in replicating the initial finding. Instead, they find something that's close or a bit different measure, only in a female subgroup or something like that. So p-hack is a version of p-hacking, but I call it shifting goalposts because it's very much changing the theory, but making it look as if you're finding evidence for the original theory. And there's some beautiful examples of this in this biomarker literature. But the final problem, I think, lies not with the scientists, but with the funders and the journals who are obsessed with novelty and who encourage us in these sorts of practices. and I'm going to be a bit mean because I'm talking about two funders who've been very good to me and looked after my research career for many years, and who are in general good eggs, as we say in Britain. But I've sat on various grant panels, and I know that if you describe research as incremental, that's a way of ensuring it doesn't get funded. ERC, who currently fund me, fund people who do groundbreaking high-risk projects. The Wellcome Trust, who funded me for most of my research career, you know, I noticed in their advice, they sort of say, they're advising you not to do this. Is your proposal just a direct continuation of existing work? And you sort of think, well, you know, don't we sometimes need people to continue existing work? So I feel this focus on groundbreaking, novel, transformational science can be the enemy of high quality cumulative science, because what's tending to happen is people are encouraged to sort of be like frogs in a lily pond and hop from lily pad to lily pad. You find something exciting, you don't develop it further, you hop off and do something else because you've got to get this novel groundbreaking result, and you never build on anything. Whereas what we should be like is termites, where we get a foundation and we sort of build on it and we get this fine structure in the end. And I've blogged about this as well. I think that, you know, I can see where the funders are coming from, because if you want to get from equipoise to certainty, you do need, I think, multiple lines of evidence. And there is a danger that you do see research where an entire body of research gets stuck in a methodological blind alley and just sort of really fails to look at the problem in any sort of new way, and just is sort of getting more and more intricate in what they're doing. And I think we have to defend against that. And I think that's what funders are really after. They don't want us to just keep doing the same thing over and over again. They want us to examine a familiar question from different perspectives. But I think that what's happened is it's gone so far in that direction that we get this sort of premature closure where we are assuming that we've got this canonized fact way before we really have evidence for that. And it's all aided and abetted by the processes that I've just talked about. And so we get in a position where nobody wants, for example, another study on ego depletion demonstrating that it exists, because they all think they know it exists, when in fact, recent big huge study done on it shows that we've been wasting time on this, as we have with many biomarkers and so on. So this is really wasteful of time and money. And so I think we need to really rethink this. And I'm just going to leave the final word to Ottoline Laser, who at the time she wrote this in the conversation was not the head of our UK RI, which is the overarching research organisation for public funding of research, but she now is, and that's very good news for Britain, because she is exactly on the right page as far as this goes. And she's written and talked about wonderfully how if you have a lot of groundbreaking research, you just have a lot of holes in the ground. She's really convinced that we need to change the research culture as well and get away from the idea that we've all got to keep making amazing new discoveries and not giving people credit for doing the hard shovel work of building foundations for good theories. So I'd end on a sort of slightly optimistic note, but I think that in general we have massively underestimated the seriousness of the problems that we've been uncovering and the extent to which they've led to research lines going on for literally decades, exploring things that don't actually have a solid basis. That's it. Thanks.
Thank you very much, Dorothy. Please, those people who are listening, participants, please put questions to Dorothy to Q&A panel. While waiting, I'll ask first question. So yeah, it's fantastic talk, and it's really encouraging in the UK. This person is the head of like UKRI, but has she done anything about sort of supporting incremental science, or is that on its way?
Well, I think, I don't know that she would say, you know, she would want to support, I don't know whether she would use the phrase incremental science, but she certainly feels, I mean, she's been the head of a big research institute in plant sciences. She's a long way from psychology. And she's picked up on the same problems in terms of, you know, this obsession with novelty and with getting things into high profile journals, and regards that as very corrosive. So she's attended, you know, a workshop that we give on advanced methods in reproducibility and given talks on this, and it's very clear that that's where she's coming from. Interestingly, she's much less interested and positively hostile to some of the solutions that some of us in psychology are after. So she and I have a lot of arguments about registered reports, for example, and whether that's good or bad. But I feel that she's absolutely right in terms of her emphasis. And she's also very concerned that science is not just something that's done by a few lone geniuses, which again is a model that I think we've operated with for too long, and which might have been true in the past perhaps. But you know, the failure to support the people who are part of a team, and I think anybody who's worked in a group knows that you'll have people in your team who are invaluable, but who don't get the kudos because they aren't regarded as the person with the big ideas, and they may have great job insecurity. And her feeling is that we've got to change the research culture to really value people who make different types of contributions, as well as you know, just the big name on the top of the paper. So I think things are going to change, but I think being aware of just how much we've wasted pursuing things without shoring up the origins is the way to get the funders on board, because they really don't want to waste their funding. And although I've singled out Wellcome Trust here as well, I mean, Wellcome Trust have been very, very good in moving towards demanding open science, for example, and open data. And they're also innovative on research culture. So I think we have, those are the two huge funders in the UK, and the fact that they're both sort of really looking at this space very critically, I think is a very good sign.
Thank you. I don't see any. Oh, yes. So Rhodes said, I'd be interested to hear the argument against registered reports. What? So
yes. Well, I mean, we should get Ottiline on. She's very forceful on this. She claims that she works in a field where it's plant sciences, where they sort of do very, very rapid. So I think it's really basically that a lot of what they do is highly exploratory. So they will be screening a load of plants to see how they respond to this, that, and the other. And I think there is a case to be made for, if you're doing highly exploratory research, that it needs a different sort of research paradigm. You don't have a hypothesis in advance. You're really, the person who's written about this really well is Stan Lazick. He's got a book on research methodology in biomedical science or biological sciences, where he says, you know, you've got the exploratory type of research where in things like drug development, you need to really take a broad brush approach, and you look at a lot of things to really just sort of try and home in on the right place. But then you have a sort of more hypothesis driven type of research subsequently. And I think Ottiline, her objection was that she felt it would make people feel everybody had to do hypothesis testing research. And indeed, in psychology, I think what has happened with registered reports is that it's highlighted how a lot of the time we think we're doing hypothesis testing, and we're not, because when you're pinned down and writing your registered report and have to formulate a hypothesis, you realize you have no idea what your hypothesis is, or how you would test it, or how your analysis would relate to it. So I think this is part of the tension. She's also been very opposed to too much regimentation in terms of things like checklists for how you should do things, on the grounds that if you get that wrong, you put people in a straitjacket and just waste everybody's time. So I think, you know, her soul is in the right place here, but she's quite an interesting person to debate these things with, because she will see it from a very different perspective, from a rather different field of science.
Interesting. We have more questions, but I'm aware of time. It's 5 o'clock and other workshops are starting. So for now, I'd like to thank Dorothy, and please join me thanking her again. Thank you very much, Dorothy. Yeah. And
I'll try and type some answers to those questions. Will they stay up?
Yeah. Okay. For now, yes.
Yeah. Okay. Well, I'll type in an answer, because it says I can type an answer, so I'll do that so people don't have to hang around, but for the record.
Thank you very much, Dorothy.
Thank you.